Welcome back to Unit 3 of our course Me22088 Vibration and Noise Control. I am Dr. C. Sendamarai Kannan, Associate Professor in the Department of Mechanical Engineering at SVC. We are now moving on to the second section of this Unit 3, that is Influence Coefficients. In this section, we will explore a different approach to understanding and analyzing multi-degree of freedom systems. As you can see on the title slide, we have a schematic representation of the three small spring system. This is just one example of the kind of systems for which the concept of influence coefficients can be very useful in determining the relationship between applied forces and resulting displacements. So let's begin our journey into the world of influence coefficients. In this section on influence coefficients, we will learn about a powerful tool for analyzing the relationship between forces and displacements in multi-degree of freedom systems. This slide introduces the concept by stating that a set of influence coefficient is associated with each matrix that we encounter in the equations of motion. Let's look at this table presented here. It shows the different type of influence coefficients based on the matrix they are related to. First, we have the stiffness matrix. The influence coefficient associated with the stiffness matrix are called stiffness influence coefficients. This coefficient tells us how much force is required at a particular degree of freedom to cause a unit displacement at another degree of freedom or at the same degree of freedom. Next, we have mass matrix. The influence coefficient associated with this mass matrix are called inertia influence coefficients. These coefficients relate the forces required to produce unit accelerations at different degrees of freedoms. Then we have the inverse stiffness matrix. The influence coefficient associated with the inverse stiffness matrix are known as flexibility influence coefficient. These are particularly useful as they directly relate displacements to applied forces. Specifically, a flexibility influence coefficient tells us the displacement at 1 degree of freedom due to a unit force applied at another degree of freedom or at the same degree of freedom. At last, we have inverse mass matrix. The influence coefficient associated with the inverse mass matrix are called inverse inertia coefficients. This relate accelerations to the applied force. In the upcoming slides, we will delve deeper into understanding and calculating these different types of influence coefficients, starting with stiffness and flexibility influence coefficient as they are most commonly used in vibration analysis. Let's now focus on the first type of influence coefficient. We will discuss in detail stiffness influence coefficient. It is denoted as K suffix ij. Stiffness influence coefficient K suffix ij is defined as the force at a point I due to unit displacement at point j and zero displacement at all other points. In simpler terms, it tells us how much force we need to apply at one location to cause a specific amount of displacement at another location within the system, keeping everything else is fixed. Consider this multi-degree of freedom system If we have displacements at various points, say x1, x2 up to xn, then the total force at any point at I, denoted as f of I, which will be the sum of forces caused by each of these displacements. The force at point I due to the displacement at point J is given by the product of the stiffness influence coefficient K of Ij and the displacement x of j. Therefore, the total force at point I can be expressed as the summation of K of Ij into xj, which is taken overall j from 1 to n. This set of linear equations relating the forces at each point to the displacement at all points through the stiffness influence coefficient can be conveniently represented in the form of matrix. Here F is the force vector, X is the displacement vector, K is the stiffness matrix, where each element of the stiffness matrix is the stiffness influence coefficient. Here in this diagram A shows a general linear multi-mass spring system, which is good example of a multi-degree of freedom system where we can apply this concept. Diagram B focuses on ith mass in such a system and illustrates the forces acting on it due to the displacements of itself and its neighboring masses. Stiffness influence coefficients help us to quantify these forces for any given set of displacements. Continuing our discussion on stiffness influence coefficients, this slide highlights two important aspects. Firstly, a key property of the stiffness influence coefficient matrix, it is symmetrical one. This means that the stiffness influence coefficient K of Ij equal to Kji. In physical terms, let me see as an example, K of 1, 2 will be equal to K of 2, 1. This reciprocity is a fundamental characteristic of linear elastic systems and can be very much useful in simplifying our analysis. Secondly, we need to consider how the concept of stiffness influence coefficient apply to torsional systems. In system involving rotational motion, we are concerned with torque and angular displacement. Therefore, for torsional systems, the stiffness influence coefficient K of Ij is defined as the torque required at the point I to produce a unit angular displacement at point J, while all other points in the system experiences zero angular displacement. But the principle remains same what we discussed with respect to linear forces or the angular forces. Now let's solidify our understanding of stiffness influence coefficients with an example. Consider this 3-mass spring system shown in this slide. We have 3 masses M1, M2, M3 connected in series by springs with stiffness K1, K2, K3. The displacements of the masses from their equilibrium positions are denoted by x1, x2, x3 respectively. Our goal is to find the stiffness influence coefficients for these systems. Recall that the stiffness influence coefficient K of Ij is the force at mass I required to produce a unit displacement at mass J while keeping all other masses zero displacement. We will determine the forces for each mass when we apply a unit displacement at one mass at a time. Let me see. Let's solve this by step manner. Let me start with unit displacement at mass 1. That means x1 equal to 1, x2 is 0, x3 also 0. That is, if we displace mass by 1 unit and keeping all other masses at equilibrium, that is 0 displacement, we need to find the forces at each mass to maintain the same configuration. For mass 1, the first spring is stretched by 1, requiring a stiffness K1. Second spring will be compressed by 1. Since x2 is 0, it is not moving, requiring force K2. Therefore, total external force required at mass M1 is K1 plus K2. This gives us K11 equal to K1 plus K2. You see that in this equation, it is written as K1 equal to minus K2. You can also rewrite here like this, K11 equal to K1 plus K2. Then, similarly, we can also see that for mass M2, if the spring is stretched by unit 1 due to x1 equal to 1, x2 is 0, the exerting force of K2 is left. That means K21 is equal to minus of K2. That means it is compressed. This gives us K21 equal to minus K2. For mass 3, the third spring is neither stretched nor compressed. No external force is required. That means K31 equal to 0. So, from this set of equations, we got it that K11 is nothing but stiffness force 1 plus stiffness force 2. K21 is minus, that is compressive of K2. K31 is still 0. Unit displacement at mass 2. This is the second step. And keeping that x1 and x3 equal to 0. For mass 1, the first spring is neither stretched nor compressed. Second spring is compressed by 1 since there is a force K2 to the right. Therefore, an external force of minus K2 is required at mass 1. This gives us K12 equal to minus K2. For mass 2, the second spring is stretched by 1, requiring force of K2. Third spring is compressed by 1, requiring a force of K3. So, the total force acting on K2 equal to K2 plus K3, summation of two stiffnesses. For mass 3, the third spring is stretched by 1, exerting a force of K3 to the left. Therefore, an external force of minus K3 is required at mass 3. That means we got K3 of 2 equal to minus K3. Unit displacement at mass 3 is nothing but we are going for mass is 3 is going to be displaced by a unit amount x of 3 equal to 1, keeping that masses 1 and 2 displacement is 0. For mass 1, both springs K1, K2 nor stretched nor compressed, no external force is needed. For mass 2, second spring is neither stretched nor compressed because no forces is acting here. Only the force is acting at M3. That means K3 is going to be stretched or compressed. Therefore, an external force of minus K3 is required at mass 2. So, K suffix 2 of 3 is minus K3. For mass 3, the third spring is stretched by 1, requiring a force of K suffix 3. That means K33 equal to K suffix 3. By collecting all this 9 stiffness influence coefficient, we can form the stiffness matrix for this given system that we collectively write it in the next slide. Yes, let's now look at the solution what we get as discussed in the last slides. This is, you can see the values we obtained for each of the stiffness influence coefficients for the spring mass system. From our analysis, we found K11 is equal to K1 plus K2, which is the force at mass 1 due to unit displacement at 1. K21 is equal to minus K2, which is force at mass 2 due to a unit displacement at mass 1. K suffix 3 of 1 is 0 because the unit displacement at mass 1 is 0. Similarly, we got the other stiffness coefficients, and finally, if we writing all these things in terms of stiffness matrix, arranging them as elements of stiffness matrix, then we got the stiffness matrix in the form of first row K1 plus K2 equal to K11. This first row second column value is minus K2. First row third column value is 0. Similarly, we return all the values. You can look this, it is a symmetry. It is a good check on our calculation that is expected for linear elastic systems. To further visualize what has been explained in the previous slides, that is the concept of stiffness influence coefficient for our 3-mass spring system, this slide presents a series of diagrams illustrating each case what we considered. Let's start with diagram B. This represents the first case where we applied at unit displacement to mass 1 while keeping masses 2, 3, 0 displacement. As we calculated, force required at mass 1 to maintain the same configuration is K1 plus K2, which is our K11. The force exerted by the spring for the mass 2 is minus K2. You can see it here, it is minus, this side it is in the negative left hand side, so it is minus K2, otherwise compressive force. Mass 3 experiences no force. Similarly, let's look at diagram D. Here we applied unit displacement to mass 2 while keeping masses 1 and 3 at 0 displacement. The force at mass 1 is minus K of 2. The force at mass 2 is K2 plus K3, and the force at mass 3 is minus of K3, that is discussed in this diagram E. Similarly, if we put mass 3 at unit displacement and mass 2 and mass 1 at 0 displacements, we got that mass 3 required a force of K3, that is positive. Mass 2 required a negative value of K3, but mass 1 not at all disturbed by nothing, any forces, so it is 0. By visualizing these scenarios, we can get a more intuitive grasp of what the stiffness influence coefficients represents. The forces needed at each degree of freedom to impose unit displacement at a specific degree of freedom while holding all others fixed. Let's move on to another type of influence coefficient, flexibility influence coefficient, denoted as A of ij. The flexibility influence coefficient Aij is defined as the deflection at point I due to a unit load at point J. Essentially, it tells us how much a particular point in the system will deflect when a unit force is applied at another point or the same point. As mentioned on the slide, obtaining all the stiffness influence coefficient in an n degree of freedom system requires solving n sets of linear equations. However, generating the flexibility influence coefficient, that is A suffix ij, is often simpler. This is because By definition, when we apply a unit load at point J, the resulting displacement at point I is directly flexible influence coefficient. If we have external forces applied at various points, say F1, F2 up to Fn, then the total displacement at any point I is denoted as x of I, will be the sum of displacements caused by each of these forces. The displacement at point I due to the force at point J is given by the product of flexibility influence coefficient A of I J and force J. Therefore, the total displacement at point I can be expressed as the summation of x of I, that is summation of A of ij into f of j, where the sum is taken over all j from 1 to n. Similar to the influence coefficients, this set of linear equations can be represented in the form of matrix where x is the displacement vector, f is the force vector, A is the flexibility matrix where each element is the flexibility influence coefficient. Continuing our discussion on flexibility influence coefficients, this slide highlights some important properties. Firstly, there is a fundamental relationship between stiffness and flexibility matrices. They are actually the inverse of each other. If we have determined the stiffness matrix for a system, we can find flexible matrix also by taking its inverse. Conversely, if we know the flexibility matrix, we can find the stiffness matrix by inverting it. This inverse relationship is quite useful as it allows us to move between two representations depending on which might be easier to determine for a given system or which is more convenient for a particular analysis. Secondly, similar to the stiffness influence coefficient matrix, the flexibility influence coefficient matrix is also similar or symmetric. This means that A suffix ij equal to A suffix j of I. Physically, this implies that the deflection at I point due to unit load at point J is the same as the deflection at J point due to unit load at point I. This is known as Maxwell reciprocity theorem and it is a significant property for linear elastic systems. Lastly, we need to consider torsional systems again. For torsional systems, flexibility influence coefficient A of ij is defined as the angular deflection at point A due to unit torque applied at point J. So, just as with stiffness, we adapt the definition to use angular quantities, torque and angular deflection to analyze rotational vibrations. Now, let's find flexibility influence coefficient for the same 3-mass system we analyzed earlier for stiffness influence coefficients. Recall the system consists of 3 masses connected in series by springs with stiffnesses K1, K2, K3 with the first mass connected to a fixed wall by spring K1. As we discussed, flexibility influence matrix is the inverse of stiffness matrix K. Therefore, one way to find the flexibility influence coefficients for this system is to take inverse of the stiffness matrix, what we derived in the previous examples. Let now start calculating flexibility influence coefficient for our 3-mass spring system. We will begin by finding the first column of the flexibility matrix, which corresponds to applying a unit force at mass 1, that is F1 equal to 1, while keeping the forces at mass 2 and 3 0. Let x1 equal to A11, x2 equal to A21, x3 equal to A31 be the displacement of m1, m2, m3 masses respectively. We can analyze the horizontal equilibrium of forces for each mass in the static condition. For mass m1, the forces acting on it are the external force F1 to the right, the force from spring K1 to the left, and the force from spring K2 to the right, setting up the equilibrium equation, that is K suffix 1 A11 equal to K suffix 2 A21 minus A11 plus 1. Similarly, for mass M2, force from spring K2 to the left must be balanced by the force from spring K3 to the right. Similarly, for mass 3, there is no force applied directly to it. Therefore, force from spring K3 to the left must be 0. Solving these equations, that is 1, 2, 3 of these equations, like substituting A31 equal to A21 into equation 2, we also get finally 0. This implies that A21 minus A11 will be 0. So A21 equal to A11, then substitute A21 equal to A11 into equation 1. Therefore, what we got? We got A11 equal to A21 equal to A31 equal to 1 by K1. All other terms are 0. Continuing with our example, we have already solved for the case where a unit force is applied at mass 1 in the previous slide. We found the displacement in terms of A11, A21, A31 equal to 1 by K1. So the first column of the matrix is set to 1 by K1. Now we find the second column of the flexibility influence coefficient matrix. This corresponds to applying a unit force at mass 2 while keeping masses at 1 and 3 0. That means the resulting displacement B A12, A22 and A32 for masses M1, M2, M3 respectively. We can again write the horizontal equilibrium of forces for each masses. For mass 1, force from spring K1 to the left must be balanced by the force from spring K2 to the right. Similarly, for the mass 2, force from spring K2 should be balanced by force from spring K3. At last, we are having the mass 3. At this case, mass 3 is not disturbed at all. Hence, through mass 3, if I substitute, I will get A32 equal to A22. Substitute this term A322 equal to A22, then this will get cancelled. Once again, we will get that A22 will be equivalent to the A12. Then substituting further, what we got is A12 equal to 1 by K1, A22 also A32 equal to reciprocal of K1 plus K2. We need to determine third column of the flexibility influence coefficient matrix. This involves applying a unit force at mass 3 while keeping the forces at mass 1 and 2 are 0. Equilibrium equation for this case is given as K1 A13 equal to K2 of A23 minus A13. We obtain the following displacements. These values represent the third column of the flexibility influence coefficient matrix. Specifically, A13 is the displacement of mass 1 due to unit force at mass 3. A23 is the displacement of mass 2 due to unit force at mass 3. A33 is the displacement at mass 3 due to unit force at mass 3. Now, let's turn our attention to the third type of influence coefficient, that is inertia influence coefficient, represented as M suffix ij. Inertia influence coefficient is defined as the impulse applied force at point I to produce a unit velocity at point J, while ensuring that all other points in the system have zero velocity. This concept relates forces to the rate of change of momentum or impulses to velocities. If we have velocities at various points in the system, say x1 dot, that means velocity, x2 dot, that also velocity, then the total impulse at any point I will be represented as f suffix I vector is summation of the impulses caused by the each of these velocities. The impulse at point I due to velocity at point J is given by the product of the inertia influence coefficients m suffix I of j and the velocity, that is x dot j, where the sum is taken over all j I to n. This set of linear equations can be represented in matrix form as shown below, where f is the impulse vector, x dot is the velocity vector, and m is the inertia matrix, where each element is the inertia influence coefficient m suffix I of j. This brings us to the end of the second section of Unit 3, where we explored the concept of influence coefficient. In this section, we started by understanding that influence coefficient provide a way to relate forces and displacement or impulse and velocities in multi-degree of freedom systems. We identified different types of influence coefficients associated with the mass and stiffness matrices as well as their inverses. We then focused on stiffness influence coefficients, defining them as the force required at one point due to a unit displacement at another. And we worked thorough an example of a 3-mass spring system to calculate this coefficient and form the stiffness matrix. We also noted the important property of symmetry in the stiffness matrix. Next, we finally discussed flexibility influence coefficient, which are defined as the deflection at one point due to a unit load at another. We highlighted the inverse relationship between the flexibility and stiffness matrices and also observed symmetry of the flexibility matrix. We once again use the same 3-mass spring system to illustrate the calculation of flexibility influence coefficient. Finally, we briefly introduced inertia influence coefficient, which relate impulse to velocity. Understanding these different types of influence coefficients provides us with valuable tools for analyzing the static and dynamic behavior of multi-degree of freedom systems. They offer an alternative approach to deriving the system matrices and understanding the relationship between forces, displacements, and motion. Thank you for your attention throughout this lecture on influence coefficients. I hope you found this section is informative. We will continue our exploration of multi-degree freedom systems in the upcoming sections of Unit 3.